third party in JUnit. Now we are focusing on third party. As an exception example, we can consider this. If any third party test engine claims to be JUnit Jupyter or JUnit Vintage, an exception will be thrown immediately, halting execution of the JUnit platform. As an error example, we can consider this occurred in the environment with Java 8. Here, warning third-party test engine implementations are forbidden to use the reserved JUnit prefix for their ID JUnit platform suite. Then org.junitplatform.launcher.core.default launcher handle throwable, etc. Now we are focusing on custom API. Here you can see the execution of a single test. The execute test method is responsible for sandwiching the actual execution call between lifecycle events. The execute text field method retrieve the URL and the expected status code and then actually execute HTTP request via a purely technical helper method. If a response is received, the method checks the actual status code and creates a test execution result dot failed result failed with an assertion failed error in case the response does not meet the expectation. If sending the request throws an exception, it is wrapped in a more technical runtime exception and text execution result and test execution result dot failed result. If all goes well, the method returns a text execution result successful result. This basically is the complete custom test engine. Now we are focusing on custom engine. Here you can see a JUnit 5 platform architecture. Contrary to the public opinion, JUnit 5 is a platform rather than simple test runner. To understand the need for such platform, it is helpful to take a look at some JUnit history. Early versions of JUnit were not designed with tool integration in mind. Due to wild success of these early versions, however, IDEs and build tools began integrating JUnit into their environments quite soon. However, because JUnit was not designed to be executed from third-party process, integrators sometimes had to rely on dangerous mechanisms such as reflection to make things work. In such integrations were naturally brittle and were very hard to change and maintain because the outside world relied upon and was coupled to JUnit's internals, even private members. In an infamous example for this coupling is the breaking of the integration in widely used IDE when a JUnit 4.x version changed the name of the private field. The situation was only exacerbated by other test libraries and frameworks mimicking JUnit structure to leverage JUnit's IDE integration. Therefore, while planning and designing the new generation of JUnit, and the JUnit team took special care to avoid coupling. As a matter of fact, the team invited representative from their major IDEs and build tools to kick off meeting in October 2015 to discuss a solid foundation for integration architecture. The main goal was to provide a different API for different groups of users, namely an engine service provider interface (SPI), JUnit platform engine for integrators of existing test engines and authors of new test engines, or a launcher API, JUnit platform launcher for IDEs and build tools to provide stable and transparent means of integrating all test engines. An annotated based API, JUnit Jupyter API for test authors, which would be similar in look and feel to JUnit 4X generation, but with the more flexible extension model. The first two are the core component of JUnit 5 platform. And this figure shows the essential parts of the JUnit 5 platform and several engines built upon it. This clear separation of concerns is fundamental to the new architecture and has so far served well to avoid problematic coupling. As a consequence, the JUnit platform has been integrated into all major IDEs and build tools using Launcher API. Similarly, the platform engine SPI has been used to integrate various test engines with the JUnit 5 platform. This allows the test engine authors to concentrate on the test definition and execution concerns and completely disregard the aspects of launching their test cases from IDEs and build tools. A special case is, of course, JUnit's own Jupyter test engine, which uses a new JUnit 5 test model. However, even this built-in engine uses only the public API and has no secret access to other parts of JUnit 5. To show how easy it is for engine authors to integrate tools with the JUnit platform, for example, you will develop a very small test engine from scratch, and we name it as WebSmoke here. Here, test engines WebSmoke, JQ, we can JUnit Jupyter in test engines, and WebSmoke and JQ and JUnit Jupyter are connected to JUnit Platform Engine SPI. SPI JUnit Platform Engine and API JUnit Platform Launcher are in JUnit Platform. API JUnit Platform Launch is connected to JUnit Platform Engine. Tool ID, build tools are in third-party tooling, and tool IDE and build tools are connected to API JUnit Platform Launcher. Here you can see an implementation of a custom test engine. Interface test engine. Test engine facilitates discovery and execution of tests for a particular programming model. For example, JUnit provides a text engine that discovers and executes tests written using JUnit Jupyter programming model. Every test engine must provide its own unique ID. Discover tests from engine discovery requests. And execute those tests according to execution requests. In order to facilitate test discovery within IDEs and tools prior to launching the JUnit platform, test engine implementations are encouraged to make use of ampersand testable annotation. For example, the ampersand text and ampersand test factory annotations in JUnit Jupyter are meta annotated with ampersand testable. From most JVM languages, being the test model on classes and methods seems a natural fit. However, other test definition models, in principle, as long as individual tests can be described unambiguously by an org.junit.platform.engine.test description implementation. Typically, a test description implementation has to be provided by a test engine author and represent a testable element of the given programming model, such as a single test, field test descriptor, or container of test class test descriptor. For the purpose of this example, we want to implement an engine that is both small and lightweight. Hence, we could contemplate alternatives to a method-based test model. One option might be to use lambdas assigned to fields, because lambdas can be considered a form of lightweight methods. This is possible since we could use java.util.function.predicate. Implementation using aptly named method boolean test tt for test execution and boolean as a success or failure indicator. While such lambdas might be a bit more lightweight than full-blown method, maybe we can take a bit further. As mentioned before, there can be different reasons for creating custom engine. Here you want to support the requirement of a special domain in such way that creating tests becomes very simple for test author. As a simple yet still useful example, we pick the domain HTTP based mock tests. In this case, the test that merely test whether a URL works. Specifically, you need a succinct way to define the URL against which the mock test would be executed. A simple means to specify expected HTTP status code. Consider the test successful if the GET request against the specified URL result in the specified HTTP status code. As for the behavior, the degrees of freedom are extremely limited. A mock test always does the same thing, namely and execute HTTP requests against a certain Since this test does not need variance in behavior, you can get rid of methods will explicitly program statement entirely, or lambdas for that matter. You can choose completely declarative approach. When you design a custom test engine, it is important to understand the contract between a test engine and a JUnit platform. This contract is defined by org.junit.platform.engine.testengine. Interface would look here: string get id, test descriptor discover, engine discovery request, unique id, and execute, void execute, execution request. Apart from some optional metadata, this interface contains the three core responsibilities of a test engine. These core responsibilities are identification. The engine must provide a unique string by which it can be referenced and differentiated from other engines on the class path. For example, Jupyter's ID is JUnit-Jupyter. Discovery. Engine must be able to inform the JUnit platform about everything it considers its own test cases. These are arranged in a tree structure with the return test descriptor. Execution: when requested by the platform, the engine must be able to execute a given execution request. This request contains a test descriptor referencing the test to be run and provides the engine execution listener to the engine. The former previously returns the engine's own discover method. The latter is used by the engine implementation to fire test lifecycle events such as execution started, execution finished. In many cases, test engines will support a hierarchical test definition model mirroring Java's hierarchical structure of packages, classes, and methods. The JUnit platform provides special support for such hierarchical engine in the form of the org.junit.platform.engine.support.hierarchical test base class. JUnit's own Jupyter test engine is itself an extension of this base class. By using this support, advanced features such as parallel execution can be readily reused by the custom engines. However, for the sake of simplicity and clarity, WebSmoke test will not use this base class. It will implement the required interfaces directly. Implementing the minimum test engine here. A test engine usually consists of the engine class itself and one or more test description implementations. This is in no way mandatory. And in this example here there are two annotations. This is no mandatory when designing this exercise here. We happen to choose an annotation based testing model. For such implementation, JUnit platform provide a good support with the org.junit.platform.commons.support.annotation support utility. Here that you can see the integration, discovery, and execution work. The discover engine discovery request, unique ID, methods creates an engine descriptor. And add test descriptions hierarchically, while engine discover request gives access to the several implementation of JUnit org.junit.platform.engine.discovery selector. Such selectors can be reference various structural elements in Java such as method, classes, packages, and whole class path or the file system, file directories, as well as JUnit's own unique ID instances. Basically, the such selectors can reference various structural element of Java such as method, such as methods, classes, packages, and whole class path. or the file system, files, directories, as well as JUnit's own unique ID instances. The test engine uses these to indicate to the requesting tool, such as IDE, what it considers test cases associated with every such element according to a specific test model. The last method here takes care of test execution. Execute execution request accept an execution request, and delegates most of his actual work to a helper class named smoke text executor. In this class, the various test descriptor variants are handled and individual tests are executed. As an example 2, we can consider this the JUnit configuration file using the Java SPI mechanism. Test engine integration. This test engine class can be immediately executed in an ID such as IntelliJ IDEA if two conditions are fulfilled. First, you need to test engine code on the class path, typically in a Maven or Gradle dependency. Second, the new engine must be registered with the JUnit platform. This is done via Java's well-known SPI. To this end, the special file must be present in the class path, as you can see in this figure. For the SPI mechanism to work, the file name must specify the SPI. Here names the org.junit.platform.engine.testengine. The file contains only one line, the fully qualified name of the main engine class, which in this case is the org.example.websmoke.engine.websmoke.testengine. This FQN must refer to a class implement in the interface specified by the file name. When the main engine class is executed in the IDE, the test result should display. As an example 3, we can consider this one using test engine test kit. Using engine test kit, a simple integration test for your custom test engine look as follows. You made a good progress with the implementation of a new custom test engine now, and you also try it out by running some example test in that IDE. Everything seemed to work, but however, as a professional developer, you would like to have a more rigorous approach to validate the new test engine. You may also want a way of running systematic and automatized test of the engine. After all, this is the key paradigm of any form of test-centered development. First approach might be to use a new test engine to test itself. While this can add some extra assurance, it does not suffice, because if you use test engine to test itself, you might fall for error masking. That's when you might not find a bug in the implementation because another buggy part of the engine hides that failure. In addition to that, the example test engine is a domain specific tool for a web smoke testing, and it is thus not capable of asserting the general correctness of software. Enter engine test kit, or more specifically the module JUnit-platform-test kit is a special integration testing tool provided by JUnit platform. Engine test kit is intended to test the interplay between JUnit platform and the custom engine implementations. The class org.joinit.platform.testkit.engine test kit provides an entry point to a Fluent API exposing test event. This offers a fine-grained assertion possibilities for comparing expected lifecycle events to actual ones. Using the example begins by proclaiming interest in your custom test engine, referenced by its engine ID, which is websmoke-test. Next, you can use one of many org.joinit.platform.engine.discovery select implementations to narrow the scope down to the example class from here. Example web smoke test. Next, execute the selected test much in the same way an IDE would. This give you an access and org.joinit.platform.testkit.engine.events instance upon which various checks can be performed. In this example, engine test kit checks the 3 tests were executed, 2 of which were completed successfully and 1 that reported the failure. This is what you should expect. You should have expected here. You can use so that the custom web smoke test can be run in an IDE just like standard JUnit Jupyter tests. One interesting feature of the JUnit platform is the ability to execute different test engine in a single run. In the past, IDEs could implement such combined execution on their own, but the JUnit platform allows this consistency for all environments that connected via JUnit-platform-launcher. To demonstrate this, add the simple JUnit Jupyter test and have it execute together with the custom test engine tests. Here the class engine test kit. Engine test kit provides the support for executing a test plan for a given test engine and then accessing the result via a Fluent API to verify the expected result. Here the engine create an execution of engine test kit.build for the test engine with the supplied ID. The test engine will be loaded via this Java service loader mechanism analogous to the manner in which test engines are loaded in the JUnit platform launch API. Here select the method selectors, add all the supplied discovery selectors. The method execute tests for the configured test engine, discovery selectors, discovery filters, and configuration parameters, and returns recorded test engine execution results. The method events or test events, get recorded events for the test. In this context, word test applies to test descriptors that run the true from test descriptor.isTest method. Assert statistics for the events contained in this events object. Started, specify the number of expected started events. Succeeded, specify the number of expected succeeded event. Failed, specify the number of failed events. The example here, the example test class has 3 test cases and 2 successes and 1 failure. As an example 4, to demonstrate that this in IDE tests for different test engines are shown in a single graphical test execution 3 in the IDE. To demonstrate this combined execution is also portable over execution environments. You can start the standalone JUnit console runner with options like following. Here the console launcher options -e or dash include engine provide ID of an engine to be included in the test run. This option can be repeated. As a result, you get a nicely colored console output here. Considering custom test engines in test engines, you can contribute your own custom engine by implementing the interfaces in the JUnit platform engine module and registering your engine. The interface test engine in package org.jnit-platform.engine and module in module org.jnit-platform.engine. A test engine facilitates discovery and execution of tests for a particular programming model. Package org.jnit-platform.engine in module org.jnit-platform.engine public API for test engines. This is in the platform. Every test engine must provide its own unique ID discover test from for an engine discovery request and execute those tests according to an execution request. The JUnit unique ID prefix is JUnit unique ID prefix is required for test engine from the JUnit team. JUnit platform launcher enforces that only test engine implementation published by the JUnit team may use the JUnit dash prefix for their test engine IDs. If any third-party test engine claims to be JUnit-Jupyter or JUnit-Vintage, an exception will be thrown, immediately halting the execution of the JUnit platform. If any third-party test engine that uses the JUnit- prefix for its ID, a warning message will be logged. Later releases of the JUnit platform will throw an exception for such violations. In order to facilitate test discovery within IDs and tool prior to launching the JUnit platform, test engine implementations are encouraged to make use of @testable annotation. For example, @test and @test factory annotations in JUnit Jupyter are meta annotated with @testable. Consult your Java doc for @testable for further details. If your custom test engine needs to be configured, consider allowing users to supply configuration via configuration parameters. Please note, however, that you are strongly encouraged to use a unique prefix for all configuration parameters supported by your test engine. Doing so will ensure that there are no conflicts between the names of your configuration parameters and those from other test engines. In addition, since configuration parameters may be supplied as the JVM system properties, it is wise to avoid conflict with the names of other system properties. For example, JUnit Jupyter uses JUnit.Jupyter as a prefix for all of its supported configuration parameters. Furthermore, as with the warning above regarding the JUnit- prefix for test engine IDs, you should not use JUnit as a prefix for JUnit as a prefix for names of your own configuration parameters. Although there is currently no official guide on how to implement a custom test engine, you can consult the implementation of JUnit test engine. So the implementation of third-party test engine listed in the JUnit 5 wiki. You will also find various tutorials and blogs on the internet and that demonstrate how to write custom test engine. Hierarchical test engine is a convenient abstract-based implementation of test engine SPI used by the JUnit Jupyter engine that only required implementers to provide the logic for test discovery. It implements execution of test descriptors that implement the node interface, including support for parallel execution. As another example, we can consider this one, execution of the main engine class in the IDE, and you can see here the fail test is in the environment IntelliJ IDEA.